All right, so today we're going to continue our discussion about the convergence in law. Last time we gave the most important result for our future lectures, which is the central limit theorem. And this is something you have learned from your undergraduate statistics classes. But here we gave you a multivariate version, and we also proved it using the characteristic function based on the Levy's continuity theorem. So as a brief recap, what the central limit theorem says is a very simple but elegant statement. We have a random sequence, and in the sequence, the random vectors are IID. So this is the most important condition here, IID. And not just this, but we also have requirement on the mean and the covariance matrix of the random vector. So we need to have the mean. Okay, oh, sorry, I should write this one, xi mu. And we need to have this one and the covariance of xi, which we write them as a covariance matrix. We need both of them to be finite, okay? The entries must be finite in the mean vector and the covariance matrix. That's the requirement. And with this, let me see. Okay, so with this, then we will have the important statement. So here we write it in this way, xn bar minus mu converge in law to normal distribution with sigma as the covariance matrix. So one thing I want to make a note is that everything that's related to n must be on the left-hand side. So n shouldn't appear here because this is a limit as n goes to infinity. If n appears on the right-hand side, then you should question your result. That doesn't make sense. Okay, so n, this part should never contain n. And everything about n should be put on the left-hand side. Okay, so last time we said that this is like a very important stabilizer. The root n is, oh, sorry about the connection issue. So we know that this part, okay, this part is going down to 0. And this part is going up as n go to infinity. So that's why they are counteracting each other. And as a result, their product is convergent to a stable distribution as opposed to a point mass. If we don't multiply the difference by root n, then we can only write xn bar minus mu converge to 0. This is a 0 vector, d-dimensional in law, right? And this is just by law of large numbers. Either the strong law of large numbers or weak law of large numbers would imply this convergence to 0 in law. And this is not meaningful. We cannot use this result for anything. So we cannot use this result for deriving the distribution because it's just 0 point mass, right? So therefore, we want to stabilize this part by multiplying something growing up, and that's actually root n. And then we can have the asymptotic distribution as normal. That's very nice. Okay, so if we think about this further, what can we say about it, right? So another look of the result. It's about what distribution? If we actually not write this left-hand side in terms of the average xn bar, instead, if we write it in terms of the sum, partial sum. So if I define Zn to be x1 multiplied to xn, I define it as the partial sum, then I know that Zn by this definition is equal to n times xn bar, right? The partial sum is equal to the average times n. And then if I write the left-hand side in terms of Zn, what would I get? So the left-hand side would become, the central limit theorem would become, so I would have Zn minus n mu, okay? And then I need to get the n out and divide that, right? So then you see here, that's my left-hand side, and I would actually have this divided by what? N. That's equal to this, and then I'll multiply that by root n. So this becomes my left-hand side. So essentially, this is equal to 1 over root n. Zn minus n mu. This is converging in law to the normal distribution. The right-hand side stays the same because I didn't do much difficult things. I just did algebra. So with this, you see that the central limit theorem can either be stated in terms of the average or the partial sum. So why do I need to make this clarification or make this connection? The reason is that this will help us think better about the more general case. That's the topic of today. So today we're going to talk about a generalization of central limit theorem. Generalization of CLT. And we call this, we give a name. It's called the Lindeberg-Feller Theorem. So what is this about? Here the generalization is to drop the identical distribution assumption. Okay, so here we still have independence. Independent, but not necessarily identically distributed. So we drop one I, that is the identical, but we keep the independent. So to understand what this is about, let me give you some examples before we come back to discuss them. So the first example we might be interested in is this. So, in statistics or probability, we often use the dice tossing, right? Or coin tossing as example. And here we are going to use it again. So think about you're tossing a coin and the outcome is binary, and you call the outcome of an nth toss as xm. And suppose that this one is following a Bernoulli distribution with a head probability Pn. So you see, as your toss goes, the probability of getting a head is changing. So Pn is not a constant P anymore. So then we want to know under what condition of Pn, that is, with what rate, how Pn changes can satisfy, we can have asymptotic normality. In other words, we want to know under what condition of this Pn we can have this root n, okay? And let me say it is actually xm bar minus summation of, say, pj, j from 1 to n, the average probability of the first n tosses converge in law to some normal distribution. This is the question that can be addressed by the Lindeberg-Feller Theorem. So in other words, we can generalize the CLT by no longer requiring the random variables in the sequence to be IID. Okay, so this is a motivating example, and we'll come back to this later. But for now, let's give it a more general notation to help our discussion. So let's revisit the CLT. So we're going to write our random variable as what? So we're going to write it actually in terms of a triangular array. This can help you understand better. So you see that when we have just one random variable in the sequence, okay, we can actually calculate its z1 equals x1, and x1 bar is equal to z1 divided by 1, right? That's the case when n equals 1. And if we have n equals 2, then we have x1, x2. And our z1 would be equal to summation xj, j from 1 to 2. And x2 bar is z2 divided by 2. This is the case for n equals 2. And let's go on to xn. Okay, we now have n random variables in the sequence. So we can define zn as j from 1 to n xj. And xn bar is zn divided by n. So this is n equals n, and so on, right? So you see that we can actually use this triangular array. Basically, every line corresponds to one value of n. So based on this line, random variables in this line, we can define its partial sum and the partial average. So you see, basically, central limit theorem is describing the behavior of the sum or the average as we go down in the row. That's the central limit theorem. So here, we want to generalize the notion for the Lindeberg-Feller. Okay, so still, we keep the notation, but to simplify our writing, that is, we want to keep the n, right? So here you see this is the nth line, this is the second line, this is the first line. So we can rewrite it as what? So we can rewrite it as x11. So the first index is for the row, that's for n. And the second index is for the position of the random variable in the row. So this one can give me z1 and x1 bar. This is corresponding to n equals 1. And for the second row, we can rewrite as x21, x22. That gives me z2, x2 bar, and it's for n equals 2. So on, we can have xn1, xn2, 2xnn. This can give me zn, xn bar, and this is n equals n. And we can continue. So you see, what we did, nothing special. We just added an index to indicate a row. And that index is to indicate n. So therefore, in the nth row, we will have n random variables. In the second row, we will have 2 random variables. So that's implied. And this is just to make our statement for Lindeberg-Feller Theorem easier. And also, this can actually give us a more general case. That is, in this writing, right, we don't necessarily have x21 equals x11. We don't necessarily have xn2 equals x22. But we can. If we want, we can add that constraint. And that's exactly the case for central limit theorem. But we don't have to. So in the Lindeberg-Feller theorem, we don't have to assume they are the same. So we are more general. Okay, so just to re-emphasize the notation before we talk about the Lindeberg-Feller theorem statement. Here, Zn is the sum of the random variables in the nth row. And this nth row is corresponding to the case of our random variable sequence that has n random variables. And that's their sum is Zn, and their average is xn bar. And we would like to discuss the asymptotic distribution of Zn as n goes to infinity. And so equivalently, once we can do that for Zn, we can do it for Xn bar because they only differ by a factor of n. Okay, so that's how we're going to pursue. Do we have any questions so far regarding the notations? Okay, it seems we're good. So then let's talk about the statement. So the Lindeberg-Feller Theorem. So what we're assuming is that those xn i's, okay? So I go from 1 to n, and n go from 1 to infinity, right? So these things are all independent. The independent assumption is still a must. And we have each x and I centered. So it's mean is 0. And we have each x, we allow each x and I to have its own variance. We write it as sigma ni squared. So you see, this is how we drop the identically distributed assumption. We don't assume them to have the same variance, but they're each of them can have their individual variance. Okay, then define Zn to be summation of x and I. N stays, I go from 1 to n. So this is the summation of the random variables in the nth row. And also, we let this notation be n squared to denote the variance of Zn. Okay, and then by independence, right? Independence here gives us the nice result. By independence, this is just the summation of sigma ni squared, I from 1 to n. That's the Bn squared. So you can see that we define it using the square notation. So when we say Bn, then Bn is the square root of that, the positive square root, and that denotes the standard deviation of Zn. So Bn, we define to be positive, okay, because there could be two roots. And then the statement comes. The statement is that we have Zn divided by Bn, and here everything is one-dimensional. So Lindeberg-Feller theorem, we're giving you the one-dimensional result, okay? D equals 1. So here, this ratio, Zn divided by its standard deviation. We don't need to subtract the mean because the Zn is centered 0, right? As x and I is mean 0. So this ratio is converging in law to standard normal. That's the central limit theorem. That's like a central limit theorem. But here we generalize it to allow the random variables to be not identically distributed. Okay, so we are not going to give you the proof for it, but here, sorry, we are not done yet. So this is the result, right? This is the result, but this is conditioned on what? Then this statement holds if. Here's the important thing. We need a condition on those sigma and i's. Okay, this is what we call the Lindeberg-Feller condition. Or we should say it's just, we can say just the Lindberg condition. What is it? So it's actually a quite complicated condition when you first look at it, but if you understand it, it's not so complicated. Okay, so the Lindberg condition says this: for any positive epsilon, this thing must converge to 0. So there's a ratio. In the numerator, we have I go from 1 to n, and it's the expectation of x n I squared times the indicator function, that the absolute value of x and I greater or equal than epsilon times bn. So it's the expectation of a product. It's x and I squared times an indicator. And the indicator says that is equal to 1 when the absolute value of x and I is greater or equal than epsilon times bn. And bn is the standard deviation of Zn. And we're not just talking about this term, but we divide it by bn squared. So you see here, what is bn squared? If we think about it, we can actually see that, see the pen. Up here. So if we think about it, the bn squared by itself, this is just equal to that. The reason is that our x and I has mean 0. So that's why these two are equal. So you see the only difference between the numerator and the denominator is that in the numerator, inside expectation, we multiply an indicator function. And the indicator is saying, okay, when this absolute value is greater than something. So we want to talk about their differences. And the Lindberg condition is saying that we require this ratio to go to 0 as n go to infinity. So it requires this. Whenever this happens, then we would have this nice result, the asymptotic normality. That's the Lindberg condition. And what is the intuition behind it? The intuition is basically saying that, okay, compared to the variance of Zn, then the contribution to the variance for the part where each x and I is super large, it's very far away from 0. So the contribution of those large absolute value x and i's must be very small. And we are making the contribution going down to 0 as our n go to infinity. So this is kind of a way to require our x and i's to be well behaving. So it cannot be too far away from 0. It must be, so it's getting away from 0, that's okay. But it gets away not as fast as the increase in this bn squared. So you see bn squared by definition is increasing with n, right? It's a sum of n variances. So naturally it goes up as n goes large. But we want to still control it so that for values that are larger than this epsilon bn, we want those values to be, we want this to happen very infrequently, in other words. So that can guarantee, okay, if I only restricted myself to those large values and look at their variances, then it's very small compared to the variances of odd values. So we'll actually get a better intuition about this later, but let's just look at this condition maybe for a few more seconds before we continue. So this is the key thing we will use to prove the asymptotic normality of any random variable sequence that is independent but not necessarily identically distributed. And we will actually be able to see that in the central limit theorem case, when those n random variables are indeed IID, then this Lindberg condition actually holds. That's a special case of that. Okay,
Excuse me,
so this
Professor?
is one. Yeah.
I just have a quick question. When you say in the conditions for this theorem that the x and i's are independent on the first line, do you mean that for each n, all the x and i's are independent, or each of the x and i's for every n and every I are independent? Because in the previous slide, when you showed that the CLT is kind of a special case of this, it seemed like each row of xni's was an independent sequence, but the rows were not independent from each other.
Right, we
The
don't need
entries
that
were...
rows to be independent at all, because when you see you see that in this statement, right, it's about a particular n. We are doing this calculation for a particular n. And then when we actually say this ratio converges to 0 as n changes, we are not talking about any random variables anymore. Because you see, when we calculate the ratio for a particular n, it becomes a constant. It's a constant ratio. There's no more randomness. So that's why we don't actually have to work about any dependence across the rows. So it's only for one row we can calculate this.
Okay, great.
Yeah. So we just need this to be independent within a row. We don't need them to be independent across rows. Yeah. Let me just make this within every row. Yeah, that's a good question. Okay, this is one direction, right? So we're basically saying that. So the Lindberg condition implies this. So the Lindberg condition implies asymptotic normality. How about this direction? If we want to go from asymptotic normality, can we say the Lindberg condition holds? Actually, this is not direct. Okay, so we need to add another condition to make it hold. So here, in addition to this statement, we need to add a condition. That is this thing, bn squared in the denominator. In the numerator, we have the max, okay, I from 1 to n, sigma ni squared. We need this to go down to 0 as n go to infinity. So we need to add this additional condition. Let me write this down to go the other way around. So what does this imply? This is saying that in the variance of Zn, right? Zn is the sum of xn1 to xnn. In the sum, in the variance, not a single variable's variance is making a major contribution. That's basically this additional conditions meaning. We're not going to have a dominant term in the row. That is in the row, right? We have xn1 to xnn. Those n random variables, their individual variances do not dominate the overall variance of their sum. That's the only requirement for this side. So we can go to a Lindberg condition. And you see that here it's a little different. This is not the same as Lindberg condition if we compare these two. Although they share the same denominator, but the numerators are different. The first Lindberg condition's numerator is the sum across the n random variables, but we are only looking at the larger values of each random variable before we take expectation. For the small values, we just mask them to 0. Here, we're looking at only the major term in the variance, right? So we have bn squared equals to sigma n1 squared plus to sigma nn squared. In those n terms, we look at the largest term, and we want that term to actually diminish to that term's ratio over bn squared to diminish to 0 as n go to infinity. So you can imagine that this condition naturally holds for central limit theorem, because in central limit theorem, all the sigma ni squares are equal to sigma squared. And bn squared is equal to n times sigma squared. When we take the ratio, it's 1 over n. And 1 over n will go down to 0 as n go to infinity. So central limit theorem naturally satisfies that. But I want to say that this reverse statement is not used so much because we care mostly about proving asymptotic normality, right? So in practice, what we use the most is we want to show the Lindberg condition is holding, and then we can prove asymptotic normality. That's it. Okay. So any questions? We are going to give you a concrete example about how we can apply Lindberg condition in practice. So as I said, we are not going to prove this theorem in this class. We give two references for those of you who are interested in the proof. Here we're going to directly show how to use it. Okay, so here it comes, an example. So in this example, we're going to use general notation. So you can see that a lot of real examples can be formulated as this general example. So here we're going to start with our IID thing. So these are IID. And they have mean, mu, and they have variance, sigma square, finite. Okay, so this is the setting of central limit theorem, but we're going to make it a little more complicated. So that becomes more general. So we define xni to be equal to some constant zni times xi minus mu. So you see, by this definition, we are satisfying the Lindberg theorem's setup. So then you see we have, by this definition, expectation of x and I is 0, right? And the variance of x and I is zni squared sigma square, and it's still finite, right? We just need to make sure the z and i's are finite. We just need to make sure this. So we're in this setup, and if we want to define Zn as in the Lindeberg-Feller Theorem, so define Zn still has the summation of x and I from 1 to n. And still Bn squared as the variance of Zn. Okay, and here we will see it's very clear that this is equal to sigma squared times the summation of z and I squared, I from 1 to n. That's the Bn squared. Then how can we make the asymptotic normality to happen? So we're going to show that we're going to give a sufficient condition for the asymptotic normality. So if we have this maximum of, okay, j from 1 to m, z and j squared, the maximum z and j squared among the n terms over the sum of the n terms, z and I square sum. If this is going to 0 as n goes to infinity, then we would have Zn divided by Bn converges in law to standard normal. Okay, we're going to show this example. And actually, this will be very, very important in some later applications, which you will see, for example, the convergence of the coefficient estimate, the asymptotic distribution of the coefficient estimate and linear regression. So those kind of results can be seen as special cases of this result. So you see that these z and i's are constant, arbitrary constant, but finite, right? So with those, we can modify our IID case to be more general. So the terms in our sum do not necessarily to have the same distribution, but they are still independent. So the independence are still kept after those transformation, but the variances are no longer equal. So that's why we cannot directly apply central limit theorem, but the Lindeberg-Feller theorem here applies. Okay, what we're going to do to show this is to show that this condition implies Lindeberg-Feller theorem, implies Lindeberg condition. Therefore, we have asymptotic normality by Lindeberg-Feller theorem. Okay, so you see this is much more applicable than the Lindberg condition. If we scroll up a little bit, you see in the Lindberg condition, what is really difficult to use in practice is this any epsilon greater than 0. That's changing, right? So we need to prove this condition to hold for any epsilon positive. That's not easy. But here the stronger condition has nothing to do with epsilon. It's just about comparing the major term to the sum. And we want to make sure the major term doesn't dominate. That's it. Okay, let's do it. So this is a proof exercise. So we want to show that the Lindberg condition holds. Okay, so we're going to use the Lindberg condition statement. So for any positive epsilon, let's write down that Lindberg condition ratio. So it's actually, I'll write it as 1 over bn squared, summation I from 1 to n, expectation xni squared times the indicator function that xni absolute value greater or equal than epsilon bn. Okay, so this is it. And now we're going to apply our special definition of x and I. That's z and I times xi minus mu, right? Because ultimately we're going to play with xi, but here x and I is defined based on xi. So we're going to do the replacement. So it's equal to 1 over bn squared. Inside it, because z and I are constants, they can get out of expectation. So I can actually write it as z and I squared times the expectation of xi minus mu squared. Okay, just a replacement. And for here, I'm going to do the replacement as well. Here, the indicator is actually xi minus mu greater or equal than epsilon bn times z and I absolute value. Okay, so it's nothing special. I'm just rewriting this as z and I absolute value times xi minus mu absolute value, and then divide z and I absolute value to this side. That's it. Okay, so we just did the first by the definition of x and I equals z and I xi minus mu. That's the only thing we did in this step. Okay, now we're going to, so here's the trick. So in order to simplify the right-hand side, we would want to make the term not related to, so we want to make the term here not related to I. See, in other words, we want to make the expectation as a constant and it doesn't change with I. That's the key thing. So once we do that, then we can get the expectation out of the sum because the sum is for I. I goes from 1 to n. So how can we get expectation out of the sum? Then the expectation must need to have nothing to do with I. And we have some hope here because xi's are IID. So if we can only have this term with regard to xi only, then I can replace xi by x1 because all the IIDs share the same expectation. And then if it's only x1, not xi, I can get it out of the summation for I. So you see what is actually holding me back is this inside the indicator function, I have the z and I. So this term has something to do with I, and I need to get this away. So you see, if this term doesn't involve I, then I only have xi minus mu squared times indicator xi minus mu absolute value greater or equal than some constant. Then I can safely replace I by 1. I can get it out. So I just need to deal with this term. And for this term, luckily, I do have something to use. That is, I want to make use of this. So if I can replace this z and I by some max, then the max will not be depending on I. Then I'm done. Okay, so the key thing, let me write it out. So the key idea is to write the expectation indicator, this term. Okay, so the idea is to, how about to make this irrelevant to I. And the question is how? Okay, so here is the trick. So let's examine the term, right? So here the key is to make this part not related to I, and then we're done. So then we can do something quite interesting. So we know that, first of all, z and I absolute value is for sure less or equal than max j from 1 to n, z and j, right? And this right-hand side is an upper bound, and this has nothing to do. This is irrelevant to I. Since we take the max, this is no longer relevant to I. So with this, you see that epsilon bn over z and I absolute value would be less or equal than epsilon bn max j z and j, right? We would have this. So as a result, you see with this and with this, then by the indicator function, as long as the indicator function is taking value 1, then the indicator function using this must take value 1. So what I mean is this. Let me write this down and that will be clearer. So basically what I'm saying is that this event xi minus mu greater or equal than epsilon bn over absolute value z and I, whenever this holds, it immediately implies that this holds. Okay, and now as we see that this is whenever this happens, right? This event implies this event, then we know the indicator function Okay, must be less or equal than the indicator function of this. And this is very important. We want to make so this is a very important trick in dealing with probability. If one event A implies another event B, then the indicator of event A is less or equal than the indicator of event B. And this can also be seen probably more clearly by Venn diagram. So if we call this event A, event B, right? Then event A implies event B means what? The Venn diagram will be something like this. So event A, set containing event A is inside the set containing event B. So that's why when A happens, B must happen. And then you can see clearly the indicator of A is less or equal than the indicator of B. Okay, so with this result, then we can have this term written as expectation of xi minus mu squared times the indicator xi minus mu greater or equal than epsilon bn over z and I absolute value would be less or equal than expected value xi minus mu squared indicator xi minus mu greater or equal than epsilon bn max j z and j absolute value. Okay, and you see I successfully make this lower bound in the indicator function not relevant to I. So by the IID, I can write this as expectation of x1 minus mu squared times indicator x1 minus mu greater or equal than epsilon bn max j z and j. And I'm much closer to what I want. So you see, with this lower bound, right, then in the Lindeberg-Feller condition, what I'm going to show here. So let me call this part the star. Then the star thing, if you can still see it, then the star thing would be less or equal than this term. I found the upper bound of it, and this upper bound has nothing to do with I. So you see, I can write it as 1 over bn squared. I get this term outside of expectation. So the expectation becomes I from 1 to n, z n I squared. Then multiplies expectation, this one, of x1 minus mu squared times indicator x1 minus mu greater or equal than epsilon bn max j z and j. Right? We're close. What is the definition of bn? If we revisit that definition, let me scroll this down a little bit. This is it. Bn is defined as sigma squared times this. Okay? By this definition, you see, I can have a nice cancellation. That is, this Bn is defined as sigma squared times Zni squared. So you see, I can have this and this part canceled. So I'm left with, you see, after the cancellation, I'm just leaving with 1 over sigma squared times expectation of x1 minus mu squared times indicator x1 minus mu greater or equal than epsilon bn max j Okay, and what I want is to show this part is converging to 0 as n goes to infinity. And this is the remaining question. Can I show this? And in order to show that, I need to realize what is still about n on my left-hand side. You see, this is not related to n, this is not, this is not. So what's only related to n is this part. So this is the only part that has something to do with n. So I want to evaluate how it changes as n goes to infinity. And don't forget that here we have this condition. Okay, this is the condition we want to start with in the beginning. We want to show this condition implies the Lindberg condition, and we're now very close. So if we can show this condition implies this, then the Lindberg condition is holding. And then we have the result, the asymptotic normality. Okay, so let's see. So since we have this max j, okay, z n j squared divided by the sum of z n I squared, I from 1 to n. Since we have this go to 0 as n goes to infinity, that's our condition. What we will have naturally here, don't forget about it, is that this thing, the epsilon bn max j z and j, we can actually write it as what? We can actually write it as epsilon times the square root of bn squared. And bn squared is actually equal to summation of zni squared times sigma squared. So I can divide the sigma here, divided by the max j of z and j squared. So you see, this is equal to this. And by writing it this way, you see, this inside the square root, the term inside the square root is the inverse, is the reciprocal of this one. As this one is going to 0, this one is going to infinity. Okay, and what does it mean if we have this go to infinity? Then the indicator is going down to 0, right? So here is the thing. Something we learned in our first few lectures will come into play. So I have the indicator this is an indicator. And the indicator is actually a random variable sequence. Why is that? X1 is random, right? So this relationship, this event is random. And therefore, the indicator is random. What is changing with n? The lower bound. So we have the lower bound changing with n. That will give us an indicator variable sequence. For every n, we have one random variable. And we already know that this lower bound is going down to 0. Going up to infinity. So we know that this event will become more and more difficult to happen. And what will happen in the sequence if we realize it? We increase n, and we draw from this. We will see that the sequence will reach zeros after some while, right? So for every realization, this indicator variable sequence will finally reach 0 after some large n. And once it reaches 0, it will stay at 0 because the lower bound is getting bigger and bigger. So therefore, this is essentially what we mean by almost sure convergence. Every realization will finally reach 0 and stay at 0. So we can say this is convergent to 0 almost surely. Does it make sense to you? Okay, great. Okay, so this is reaching 0 almost surely. And so if I multiply this by this part, it's still reaching 0 almost surely, right? Because this is not something blowing up. It's not going to infinity. So if I multiply by this, x1 minus mu squared, so this whole thing is still converging almost surely to 0. Okay, but what I need is not almost sure convergence to 0. What I need is the expectation convergent to 0. So how do we go from almost sure? Yes?
I just have a quick question. So are we allowed to just claim in general that with an indicator variable, if the bound goes to infinity, it converges almost surely to 0, or do we have to formally prove that, like in practice?
Actually, I think this, I think what I said just now is a proof. So basically, this is based on the definition of almost sure convergence, right? Almost sure convergence basically is saying that, okay, so what we mean is that the convergence, the probability of convergence has probability 1, right? The probability of that convergence equal to 1. And here, where I'm just saying that for this indicator function, as this lower bound goes to infinity, you can always find an n in your sequence. After that n, then all the xi minus mu are not bigger than this. So therefore, you would not we're not bigger than that lower bound, then this indicator will be 0. So you can write this in a mathematical way, but still it's the same as what I just said. So because once it stays at 0, it will be 0. And right, if it's 0, 0, 0, then that's convergence.
Right. Okay.
Yeah.
Thank you.
But to be exact, you need to write it in terms of that epsilon delta language. So here epsilon is used, right? But you can use delta. You can say that, okay, for any delta positive, I can always find a big N such that I would have x1 minus mu less than that epsilon b big N over this, right? So then I have that, yeah.
Okay, got it, thank you.
Yeah. No problem, yeah. We just need to prove every realization converges. That's it. Okay, so we have almost sure convergence. Then how do we go from this almost sure convergence to the expectation convergence? This is something we can use for, we talk about it. We didn't prove it. The dominated convergence theorem that can be used here. So by the DCT, dominated convergence theorem, here the indicator is another thing to use, right? So this thing is multiplied by indicator is dominated by this thing itself. So x1 minus mu squared times the indicator, know this, is dominated by x1 minus mu squared. Okay? And by our condition, we know that this right-hand side, x1 minus mu squared, is equal to sigma squared, and it's finite. So we find a random variable that dominates it, and the random variable itself has finite expectation. So therefore, we can go from almost sure convergence to convergence in expectation. So we would have this x1 minus mu squared times indicator x1 minus mu greater or equal than this. Expectation converges to 0. That's it. That just completes the Lindberg condition. We proved the Lindberg condition, so we proved the asymptotic normality. So I think, I can stop here. So this basically completes the proof. So Lindberg condition Lindberg condition is checked. So we have that. So I want to use this. I spend the time to actually show this because I want to make you aware how we can actually prove that the Lindberg condition holds. And here we give you an example. And I will say this example just applies in general. So whenever we want to deal with this complicated form in the Lindberg condition, so I'm coming back here. Whenever we want to deal with this complicated form in the Lindberg condition, what we want is trying to make the expectation not related to I, and then get it out. And then we can show it much more easily. Otherwise, every term here is related to I. That makes showing this thing is not easy. It's quite complicated. Okay, so again, we see that even though the Lindberg condition is regarding random variables that are not necessarily IID, but in this example, we see that we still go back to the IIDs, the x1 to xn, they are IID, even though xni's are not IID. So this is here, right? So you see, we start with non-IID x and I, but we quickly get back to xi that are IID. And with IID, the nice thing is that whenever the expectation is only about xi, we can replace xi by x1. So then the expectation becomes not relevant to I, and we get it out of expectation. That's the key trick here. And we will actually see this again in another example very soon. So, but for today, let me try to give you a stronger condition before we finish. That's what we call the Lyapunov condition, which is stronger than Lindberg, but easier to check. So in practice, if you can check the Lyapunov condition, you don't need to check the Lindberg condition, and then you're happy. Okay, so let's see the stronger condition. What does it look like? The Lyapunov condition. So this is basically says that if you can find a delta positive, so this is existing. There exists such a delta that we have this. So basically, it's still a ratio. In the numerator is I from 1 to m, expectation of x and I to the power 2 plus delta, right? It's a power greater than 2. Numerator in the denominator is bm to the power 2 plus delta. So if you can show that this is convergent to 0 as n go to infinity, you're done. So this is much easier to check because it doesn't involve epsilon. You're not going to show that for any epsilon. What you only need is to find such a delta to make this hold. If you can do it, then you're done. So here is the important result. We call this a lemma. And this lemma is saying that the Lyapunov condition implies the Lindberg condition. And because of this, you can go from the Lindberg condition to have asymptotic normality by the Lindeberg-Feller Theorem. So that's why we can check this. If that's more convenient, we do it. And how do we actually have it, right? This is something quite magical. Why do we have this? Still, we can actually show that this proves the Lindberg condition quite straightforward. Let's do it. So we can prove this basically as one line. So in the Lindberg condition, we don't forget we have that epsilon positive, right? So the first thing we have is, so in the indicator function, if you recall, in the indicator function, we have the x and I absolute value greater or equal than epsilon times bn. And this implies what? This implies we would have x and I divided by epsilon Bn. This is equivalent to this, greater than 0. We just divided. And this implies what? So if this hold, and I raise the left-hand side to a power of delta, positive delta, then I still have that power greater or equal than 1. So this implies that for delta positive, I would have xni epsilon bn to the power delta greater than equal than 1. That's it. So you see, then by Lindeberg-Feller condition is this. Expectation xni squared indicator xni absolute value greater or equal than epsilon bn. Okay, what I can do is that I can multiply this by this. Because this is bigger or equal than 1, I can write this is less or equal than, I multiply by epsilon to the power delta times bn to the power 2 plus delta, because I'm doing the multiplication. And inside, I have summation I from 1 to n, expectation xni to the power 2 plus delta, sorry, I forgot the absolute value. Yeah, 2 plus delta, and still indicator function xni greater or equal than epsilon bn. Okay, so I didn't do anything special. I just multiplied this part by this. And because this holds, whenever this holds, right, I can actually get this xni delta into my expectation. Why can I do that? Because this is controlled by the indicator. So when the indicator is taking value 1, this hold. So I can do the multiplication. When the indicator is taking value 0, it's 0 anyway. I don't care. So that's why the indicator allows me to move this inside the expectation. You can think about this more carefully. This is still random for sure, but I know when this expectation is not, when inside expectation is non-zero, which means the indicator is taking value 1, then this hold. So I can do the multiplication. And then I can further control this by changing the indicator to 1, right? Indicator is always less or equal than 1. So I can safely have another upper bound that is summation xni absolute value to the 2 to the power this. Right? I can drop the indicator by changing it to 1. And that's it. So therefore, you see that if I can show for at least 1 delta, the right-hand side is going to 0, then this is going to 0 for any epsilon. And that's the Lindberg condition. So if there exists delta greater than 0 such that the right-hand side is going to 0, right? Then the left-hand side is going to 0. Right, the right-hand side going to 0, this is the Lyapunov, and this is the Lindberg. That's it. So that's why we only need the existence of such 1 delta, and we're done. That will make our right-hand side go down to 0. So I think in this proof, a very important trick is how do we deal with indicator function? So you see, indicator function in probability is very, very useful because you can actually easily multiply random variable as if it's constant inside expectation. The reason you can do it is because you are basically protected by the indicator. The indicator gives you, okay, you only need to worry about when the indicator takes value 1. That is when the event is happening. So you can basically assume, okay, this event happens for sure, and then I can do the multiplication. Because when it's not happening, you are guaranteed by 0, so you don't hurt. And another useful thing for the indicator function is that you can always upper bound it by 1. You can replace it by 1, and then you can have an upper bound. That's also very useful. Okay, so that's the Lyapunov condition. And then we can see that here, we can conclude with a quick example about using it. Okay, so this is the motivating example we give in the beginning about the non-IID Bernoulli. Well, we have here Xn following Bernoulli Pn. Okay, and then we can show that we can find a sufficient condition for the asymptotic normality. Okay, so here, let's do the centering. Let's define Yn to be Xn minus Pn. You see, by this definition, we would have expectation of Yn equal to 0. And the variance of Yn is equal to still the variance of Xn. So we know that this is equal to Pn times 1 minus Pn. Okay, and so here basically Yn is like our X and I. So it's our X and I, right? Here we have this. So probably I can write it out further to help you see the connection. So here, if we write this in a triangular array, what we have is Yn, Y1, and Y1, Y2, to Y1, Y2, to Yn. So we are back to the case where these things are equal, 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 but still every row has n random variables. So we are in this case. So essentially, you can consider our writing before, right? What's X and I, and what's that? And so here the Zn is still I from 1 to n, Yi. Okay, we just want to use that same language. Then what's Bn squared? Bn squared is the variance of Zn, okay? And it's actually summation Pi 1 minus Pi and I from 1 to n. That's it, that's our Bn. Okay, and what else can we say about the Lyapunov condition, if we want to show that? Then you see the Lyapunov in this case is to find a delta, find delta greater than 0, such that we can have the summation I from 1 to n, and it's the expectation of using the same notation of absolute Yi to the 2 plus delta divided by Bn to the power 2 plus delta go to 0 as n go to infinity. We just want to find such, we just want to find such a delta to achieve this. How do we do it? So in fact, I would say our first try would be to try delta equals 1, because that's an integer. That's the smallest positive integer. So that's why that will be our first try to see if we can do it. So let's try delta equals 1. And essentially, we can actually see that expectation of yi to the power 2 plus 1. That's cubic, right? We can actually easily write it out because every yi is Bernoulli. So, by y, it's xi is Bernoulli. Okay, let me further write it out. It's xi minus pi to the power 3. So if we write this out, we can easily see that it's either xi take value 1, right? That would become 1 minus pi to the power 3. And that happens with probability pi. So it's equal to pi times 1 minus pi cubic plus the other case, xi equals 0. 1 minus pi to the times negative pi to the power 3. That's it. Okay, so I guess we are running out of time, so we will actually stop here, but I'll leave this for you to try it out, to see how we can, what is the sufficient condition for the PIs so that the Lyapunov holds, so that the Lindberg condition holds, so that we have the Lindeberg-Feller theorem. So we can find a strong condition, that's okay, but as long as it's sufficient, you can say, okay, whenever the PIs follow this relationship, then we're good. Okay, so let's stop here and we'll continue and finish this on Thursday. And we will give another 2 examples, I think, about the application of Lindeberg-Feller theorem on Thursday. And then we will talk about another generalization of the central limit theorem. That is, what if we dropped the independence? And what will happen then? Okay, so I'll see you on Thursday. And so this is, yeah, I'll see you on Thursday. And
thanks, Professor.
no problem. And so let me stop the recording.